Recording on progress. Okay. Okay, so routing. Routing is the idea of finding out where to go with a packet, with information. So now we're talking about the network layer. We're not talking about the data link layer. Data link layer talks about communicating with a neighbor. There's no routing. We have one link, we send, put the data on one end, gets to the other end, or broadcast it to everybody, depending on the type of local area network. Now we're talking about going beyond this neighbor. Could be the machine next to it, or the machine on the other side of the world. How do you find that machine? So there are different types of routing that has been used over the last 50 years, I guess, or 40 years, but also some are still in use today. So, first type of routing is known as the fixed routing. So fixed routing is a routing that's done once, that's done manually by hand, and it doesn't change frequently. And the opposite of fixed routing, sometimes called static routing, is the dynamic or adaptive routing, sometimes called dynamic or adaptive. But the adaptive part means it'll tell you where's the best route, but if things change, if this part becomes busy or crowded or slow, it might change the route. So it will adapt based on some certain circumstances or some factors that happen within the network itself. Maybe too much traffic, or maybe a breakdown of a link broken down, or a router, or they didn't break, they just were switched off or switched on. So if there's any change, then it might adapt. But the fixed routing, it doesn't change. And in general, in order to do routing in general, you need information. Just if I say to you, remember, routing is trying to find out the cheapest or the most efficient way to get from one point to another point in the network. So if I do ask you now, if you, for example, you want to travel to, I don't know, Indonesia, find me the best route. First, the best route may have so many different meanings. It could be the cheapest route, it could be the quickest route, it could be the safest route, it could be any number of things. We just say the best, and for now, as a general word, or we say the cheapest or the lowest cost. But the lowest cost, it could mean so many things, not just in time. It could be in money, on time, or cost, or safety, or whatever it is. And usually, in order for you to do that, and that's exactly what happens on networks as well, in order to find out the best route to Indonesia from here, you might have to collect some information. All the different airlines that fly, or boats, or whatever it is, how much they cost, when do they leave, and all that. And once you have all that information, then you can start testing them out, finding the shortest route. You could go through London, and London maybe, I don't know, Dubai, Jakarta, or something like that, or you can go through Rome, and I heard they have a good route through South Africa as well. So there's so many different routes you must find out. And then once you finish calculating and find out the cheapest, then you decide where the best route is. And that's normally what happens on network. Collect information, calculate the best route, and then start working on that. But then things change on the network, then you keep collecting more information again, recalculating, update your routing routes or tables, and then use them for a while, and then this keeps happening all the time. Collect information, update your routes, use them, and then do that every few minutes. In some networks, they do it every few minutes. Some networks only when there is a change, a major change. So that's really what the adaptive routing is. Collecting information, updating your routing tables. Routing tables are the ones, the guidelines for those who want to travel. They say, we've already done that work for you. Here is the best route to go to that, in that direction. So we'll start with the fixed routing. The static or fixed routing is a routing technique that's done once most of the time. We don't do it every few minutes or every few hours or every few days. Sometimes we do it once and it runs for a year or a couple of years without any change. That's called fixed routing or static routing. And usually it's done manually. We don't need a program to do it. And also it's done by manually, that means by a person. And usually it's the network administrator or somebody, that the network administrator would enable. And usually you need a table, so you create tables. First, you also need to collect the information. This is like if we only have 3 or 4 airports to travel to, and we say, okay, guys, find out the cheapest way to go. Cork, Dublin, Belfast, London. That's all we have. And then you can plot them out, find out the prices, and you say, okay, you want to go from Dublin to whatever, maybe Belfast. Maybe you can go straight, but it's cheaper to go through London and back to Belfast, maybe. So if we're looking for the cheapest cost. So that's how it's done. So fixed routing, generally, you need a table. You need to plot out your network. You plot the network out, do measurements. You can do measurements, you can send, if you do a few tests on the network, you can send packets and you get the response back, and it'll give you the exact time it takes for that packet to travel. You can plot out these delays. So let's suppose just you got these numbers, 4 milliseconds to send a packet to B or back from B to A, and so on. And sometimes you get different readings in different directions. But for now, for simplicity, we'll say it's the same cost going from A to B or B to A. And then once you can plot out, and these are supposed to be routers. The A, B, C, D, and E here are supposed to be routers, and they might have names, but also they might have IP addresses. Well, they will have IP addresses, but we'll refer to them with names at the moment it's easier. And every one of these routers has or should have a routing table, and usually you can log into it from anywhere on the network. You can log into each router. If you have the correct password, the correct access, you'll be able to log in there, get in there, and create a routing table or update the routing table it has and save it, and it will save it. You won't have to change it again. It will be saved onto its hard disk, and every time it starts, it picks that routing table, and there it is. This is like doing the hard work for somebody who works in a travel agent in an office for holidays, and they don't know anything. So the next day, a customer comes in and says, I want to go to Dubai. I want the cheapest way. You already have a map like this. You say, oh, if you're going to go to Dubai, that's what it'll cost you, and you'll have to fly to London first, or something like that. And that's what a routing table is. Every routing table consists of 3 columns. The first column is the actual destination. Where do you want to go? So now this is an example of a routing table for router B, for this router here. You need to fill this. So to fill this, first you have to put all the different routers that are available that are directly accessible or that are within the network. Sometimes it's not directly accessible, but it's still within our range that we want to cover it. Of course, you don't have to cover every router in the world, like the ones in Indonesia and the ones in America. No, you only cover the ones you are dealing with it locally. And if you need something that's not around, then you will allocate a default router. There's one of these routers that will connect us to the outside world. Maybe there's a router that connects us to Europe and another router that connects us to America and Canada. So you need to know which ones. But for now, let's just assume that is our network. Let's say in Griffith College, we have 5 or 6 routers, and we have hundreds or thousands of computers, and we want to set it up. So this is the way to set it up. In the routing table, in each router, there are 3 columns. So you need to put all the addresses of all the possible routers that you need to go to. Remember, routers don't necessarily need to travel or send data themselves most of the time. It's very little if they do send. It's users that are connected to this router. Let's say router D here might have dozens or hundreds of users connected to it. User B also has users. So users are connected to what we call gateways or routers or modems or whatever the devices, that the names that are used to connect users to. So a lot of users' machines are connected to this router and that router and so on, or connected to a smaller network that's connected to this router. So it's the users outside the network that will be sending information to other users on the other side of the network. Okay, so this is what you need to be thinking or aware of. A user here wants to send information to somebody at this user, a user that's connected to this router. So every message you get from, say, from a user, when you're at router E, for example, you want to find out what address you want to send it to this router A, because the other user, the final destination, is connected to this router. So you only need to send it to wherever this router is. And usually it's by network, wherever this router is also connected to another local network. So usually it's the address. But let's just find out now. It's easier to think of them like cities or airports, and you want to go from B, you want to go to A, from B to D. And once you put down all the routers that are available, and you start now starting from router B, let's say, if your destination, if you are now at router B and you want to go to A, find the best way, the shortest way, or the one with the lowest cost. So there are hundreds of ways, well, at least dozens of ways here. You can go to EDA, that's one route. You can go to ECDA, you can go to CEDA, you can go straight to A, from B to A, you can go BCA. So there's so many ways. Try every possible one of them and find out what's the total cost. This is like you're here in Dublin and you want to go to, I don't know, what's this one? Rome. You can fly direct to Rome. It can cost you 400 or 400. You can go to London for 200 and then 100 to Rome. So there's so many. Or maybe you go to Paris. From Paris you go to another place and then Rome. So you can go to so many different routes. Find out the cost, this one with the smallest cost. And the one with the smallest cost now here, we find it's going through C. So if we go through CA, that will cost 3, and that seems to be the lowest cost. Because if we go through E, it will go 2 plus 1 is 3, and 2 is 5. And if we go directly, it's 4. So the cheapest way is to go through C and then A. You don't have to tell, you don't have to put in the routing table. For example, E was the shortest route. You don't have to say, you go to E and then you go to D and then you go to A. No. All you have to just say, what's your next destination? The only first available hub, the next hub. So once you select that, so the second column will give you the cost. You put in the cost, and the next column you say, where's the next destination? Not the final. But if you want to go to A, you go straight to A, you put A there. If you want to go through E and then somewhere else, you should only write E. You don't have to write where else. Yes?
Exactly exact cost. Time.
Say again? The cost? Okay, right, I mentioned it a little bit earlier. The cost can be a variety of things. It can be delay, it can be actual cost, it can be a level of security, or this line always breaks down, that increases its cost, for example, historically, even though now it's not broken down. So it's a collection, it can be a collection of things. But now for fixed routing, we've decided to take measurements. This is now fixed routing, where you do it manually. Fixed routing, if you are asked what is, or tell me about fixed routing, it's only done for small networks. It's done manually, normally by the network administrator. And you need to collect the delays or whatever, the figures, the costs on all links between all nodes. And then try and work out the shortest cost. And that's what we are doing right now. From every node, now we're doing the example from B to every other node. So the next in the list, we're in B. Remember, we're router B. You got a packet that says I want to go to A. Best ways to go is you send it to C, and that we know in advance is going to cost you 3 to reach A. Now, what about if you get a packet that wants to go to B? somebody who's been sending a packet and you got this packet, and your routing system or your network layer opens this packet and says, oh, you want to go to B. You're already in B. So the cost is 0. You have no more cost and you don't have to go anywhere else. Your final destination is going to be on one of the direct neighbors here. So we hand it over straight to the final user. Now, the next one, if you want to go to C, what's the best way to go to C? In this case, we found, of course, you can go to C through E, cost you 3. Through A, it cost you 5. Through A, D, and then C, it costs you, an arm and a leg, let's say 6, 9. So the cheapest way for now, it's 2. So straight to C, and there it is. Straight to C, it costs 2. If you want to go to D, again, there's so many ways to go to D. There's 2, 1, and 3, or 2 and 1 through E, then it costs us 3, and that seems to be the lowest cost. And if we want to go to E, again, you can go straight to E, but yeah, that's probably the cheapest way now. And there it is, save that information, and the table is saved. Now E is ready to receive any packet in this small network. Now, you need to do that for A as well, for C, for E and D and so on. Okay, and this is called fixed routing. And that's what we do manually. It's called fixed routing. The rest of it is done almost the same way, but it's done automatically. And we'll talk about the other systems. So let's look at this first. Fixed routing. Everybody okay with this? Can you do me, please, can you do the router F for me? What is the routing table for router F? Can you flush it out? You have 1 minute or 2 minutes to do it. So just to realize how simple it is, and this is a fairly biggish network. You wouldn't do it on bigger network than this manually. Manually difficult. Also, another statement to add manually is that you do it once, you don't have to change it. Unless a major change happens, unless you buy a new router and you install it, well, then you need to go around and update your routing tables. Or something breaks down and breaks down for a long time, so you can't update your routing table. But sometimes they do fixed routing, and for years, for months, it never changes. And the good thing about it, you don't have to do it again, and you don't have to exchange any information again. Remember, in other routing systems, we have to keep exchanging information to keep it up to date. With this system, yeah, it doesn't get updated, but routing is not great. So I'm going to go to this one. It's the same, but this is what, anytime you're asked to create a routing table, 3 columns. You need 3 columns. You start with a table with 3 columns. The first column is called the final destination. It's the same network. Yeah. And the second column is called the final cost, or the cost to reach the final destination. And next up is, where's your next node? Yes.
A root cost is the same, going by, oh no, it's not the same. I think from F to A, you go through E and then D or C. 2 different costs are the same. So which would you choose?
You try to choose, okay, some cost is, if you're traveling, say from here to Rome, right? And you can go to London, Paris, Rome. Or you can go straight to Rome, or you can go Madrid, Rome. And if they're all the same cost, which one would you pick?
If it was a direct one, I'd choose the direct one.
Yeah, so it's the one that with less flights, and here again with less hubs. Every time you go from one machine to the next, you go to hub. So it takes you 5 hubs, and another route takes you 2 hubs, and they're the same cost. Go for the one with the less hubs.
Also the same number of hubs. Because that's
what
the case here.
Either then, it doesn't, So always go for minimize. Things that are used to minimize, sometimes you find out the reputation of a line. How often does it break down? Let's say the last week it broke down 3 times, and the other one didn't break down at all. Well then, increase the cost on the one that breaks down. Or availability, or security. Sometimes you go through a line, it's cheap, but we always lose packets. We go through another line, it's like flight. You fly through some route, and you lose your suitcases, your bag. Another route, you never lost them. So if an airport becomes famous of losing suitcases, passengers will start avoiding it. So it's pretty much the same on networks. It's like traveling and finding out the best route. So a lot of factors are taken into consideration. In fact, what Cisco does, it takes the breakdown, the delays, number of hubs, the speed of the links as well, or the capacity or the bandwidth of the link, and put them all together and hands you one number. Like some of them contribute 20 points, some of them contribute 70, some of them contribute 5. And once it finds a number, it gives you the number, say, okay, you go that from here to there, it costs you 120. And that's just a cost, the general number of costs that everything has been taken into consideration. It's like, again, when you travel, you might travel cheaper, but then the comfort, maybe in the airplane that you travel in has comfort. So you might increase, or that will go towards, I might prefer that one. So you reduce its cost. Even though it costs a little bit more, you might say, no, but it's more comfortable. Or there are better services in there, or whatever, availability. You might fly with an airline like Lufthansa, it's going to be on time 100% of the time. So you might fly with it rather than, some other airlines that are famous for being so late or cancellations of their flights. So that would be taken into consideration as well. Okay, so everybody's done this. Okay, give me an example. Have you finished? What's the shortest route to go to A from F? And what is the cost you got?
So I got 4.
4?
And that's from F to E to B to C to A.
Okay. How many hubs is that? 1, 2, 3, 4. Anybody else got any better cost than this?
No, same but different distance.
Yeah?
Yeah, it's
The same?
the same cost, but the hop goes over G.
Anybody got a better, sorry, same cost, but what?
Over G and then D and then A.
Yeah, that's better. Why is that better? Because the number of hops. So this way, going this way is also 4. To G, D, A. So that's 1 plus 1 plus 2, that's 4. Same as your first cost, 1 plus 1 plus 1 plus 1, that's 4. Going through E. But going through G has an advantage. It only goes 1 hop, 2 hops, 3 hops, and you're there. It's like you're flying to Indonesia. You can go through London, Rome, Indonesia. Instead of having to go London, Rome, maybe Dubai, and then Indonesia. So less number of hops, less stops, they call it in the airlines. But here we call them less hops. So if you find things that are same cost, try to find something else that you can put a preference, that one of them is slightly better than the other. If you are told this link breaks down frequently, well then avoid it, even if you get the same cost. And sometimes you're told this link is twisted pair, this link is fiber optic. Well, go with the fiber optic. It can handle more traffic. If traffic builds up, it will still perform better than twisted pair. So that's what actually is done in Cisco networks. But now you're doing this manually. So now, okay, this is what I have here. A, it's better to go through G with 4 hops. With B, if it's from F to B, you can go straight, cost you 3. You can go through G, it costs you 1, 2, 4, and 5, 6. But you can go through E, it costs you 2. And this seems to be the smallest cost and number of hops and all that. Okay, guys, so this is just a quick idea. Now, the problem with today's adaptive routing algorithms. So now, just you need to know what is an adaptive routing algorithm and what's a fixed or static. The fixed, you do it once and you never change it again. With the adaptive, you keep updating it. In some networks, they update it every 3 minutes. Every 3 minutes, collect information, all the costs, and then you start, have an application that runs and finds out the best route. What you've done manually there is a program that will do it. And then update the routing tables for all your local routers or for your individual router. Every router receives information and updates its own routing table. So that's an adaptive routing system. Adaptive routing system is a system that will update its own routing tables based on changes in the network. That's the definition of an adaptive routing. A fixed routing is a routing system that's done once. Normally it's done manually. Because it's manually, it can only be done on small networks, and it will not change again or update unless really something major happens. But sometimes it runs for months or years without any change. That's the fixed as opposed to adaptive. But the problem with adaptive, guys, well, no, adaptive routing is the most used system today, right? Almost all networks use adaptive routing, especially complicated big networks, they must use adaptive. And because things change, sometimes you get a lot of traffic happening in one area, causing congestion, the adaptive will start diverting traffic away from that area until the measurements, the next measurements we get, we see that delay has gone down, then we can re-adapt again. So adaptive is the better one, that's most used. But the problem with adaptive routing is that it collects information. Let's say every 3 minutes, all routers exchange information because every router knows who is in their vicinity, or some routers, every router has its own routing table and tells you, here's my routing table, give me yours, I'll send it to that one. Everybody sends their routing table to everybody else. So there is a good bit of information exchange. Not user data, this is system data, routing information. And that's a cost. We don't want to do that. These links that we have, they're there to deliver user information, not system information. Okay, so this is like you have a bus that runs, that's supposed to make money, but then you get 6 seats there for the mechanics, just in case the bus breaks down. The mechanics don't pay money, they take those seats that used to bring you in money. Same with links, communication links, they're there to deliver data that belongs to users, not to deliver data that belongs to the system, because they take off the user's kind of capacity. Now, so that's one problem. The other problem is that every router has to stop a little bit and start processing this information that it collects and builds its routing table. And that's not an easy process. It takes a lot of processing. That processing as well should have been used in delivering packets around. And we call that forwarding packets. So adaptive routing has a lot of cost. First, cost on the transmission channels, the capacity of the channel, because we do have to collect information and exchange information. And then this processing that takes a lot of time or a lot of processing power to update the routing table. So somebody came up with the idea and said, listen, I can deliver any packet anywhere it needs to go without any information, without any routing tables. I don't need to keep routing tables, so I save a bit of memory. I don't need to exchange information, so I can save transmission channels. And I don't need to do any processing to update those routing tables. So it's a fantastic system. It's called the flooding. How could flooding find out and know about every destination? It's simple, they say. Every packet that you get, you send it in every other direction. Look at this example. Let's say we get a packet that wants to go to E. There's flooding. A gets a packet from a user, send it to every other. Send a copy to every other router. Now this router gets a copy, it will send a copy to every other router, and there it got to be immediately. So you don't really need routing as such, really clever routing. You can deliver any packet you want through using the use of flood routing. So flooding, if you're asked to describe it, it's every packet you get on one link, send a copy on every other link. You are guaranteed you're going to reach every destination. And if every router does the same thing, so router C gets a copy, passes it everywhere. Router E gets a copy, sends it on every other link. You're going to cover every point. And we don't need to keep routing tables. We don't need to update routing tables. We don't need to exchange information. Anybody can see an issue with this? Can you see a problem with this system?
Well, it's doesn't imagine very easy to load.
Yeah. First thing, flooding will overflood the system with too many copies. Because remember something else, this copy that C got and sent a copy that way, E will send a copy every direction, a copy will come back, and D will get a copy on this link, it will send a copy that way, and there you are circulating copies. Endless way of building up too much information. So, as part of flooding system, they said the best way to do it, we use something called TTL, time to live. How do we get rid of all these packets or all these copies of these packets? Well, they said, let's use a system and they call it time to live. Every packet that's created or every packet that enters our network, it's stamped on its header. There's a field on every packet header and we call it time to live. And you put the number of hubs this packet is allowed to move in our network. And every time it moves, we decrement that. So for example, you look for the longest route for this network. For this network, the longest route, you go from A to F, that's probably the longest. 1, 2, 3. So there are 3 hubs. No packet should stay there more than 3 hubs. Let's say 4. So we put every packet that comes into our network, we stamp it, we give it stamp 4. That means you're allowed 4 hubs. Let's say a packet came in here to A. We stamp it with 4 hubs. You say, where do you want to go? We don't know where you want to go. Send a copy everywhere. But first decrement a number before you send it. So instead of 4, we decrement it, now it's 3. So the copies that went have the number 3. Every router here, first thing it gets a copy, it decrements its header, the time to live, to 2. And let's say C got this one. It looks at it and says, oh, you have 3 lives left. Well, let me take one now, so you only have 2 lives. Let's send a copy that way, this way, this way. So now this one got here, the copy with 2 lives. He looks at it and decrements it. You have 1 more life and sends a copy everywhere. When it gets those copies that went around, they'll be decremented here, the copy will be decremented here, this one will say, hey, you're 0. You're not going anywhere, finish, discard this packet. So we eliminate, or packets gets discarded based on the number of hubs that they spend in the network. Starting with, if we create a packet, we'll put that number on it and starts losing lives every time it jumps from somewhere to another. So if we make a copy of it, it'll have the new number. Yeah.
So if a node receives a copy that's already previously received from another node, it recognizes it, it doesn't send that one as well, right? Okay, speed.
Okay, that's a second option. For now, this is the time to live works like this. Any packet. Now flooding works like this. Let's start with flooding. If you receive a packet from anywhere, send it on every other link except the link where you received it from. So, but if you get it again, that's another problem. You receive from this one, you get the same copy. At this stage, you don't know. So this guy gets another copy and will send a copy everywhere. So how do we eliminate that? By putting a maximum number of the number of hubs. So when they reach 0, they're discarded. You don't send them anymore.
There are still way more transmission costs than that normal.
Say again?
There are way more transmission costs.
Yeah, you're right. Yeah, so this one has a higher transmission cost. Yeah, but it has other advantages. For example, earlier on we found where's the best way for F to send a packet to A. Somebody said this is the quickest way. 1, and then 2 here, 4. So anytime a packet arrives to A, to F or G, it will be sent in this direction. What happens if this link breaks down? In the fixed routing, that's it. No more packets can go from F or G back to A because this link is broken down. With flood routing, hey, yeah, this link breaks down, it's no problem. The other copy will go that way, and this way the other copies will go this way, and eventually they'll all get there. So flood routing is more robust. And it also, if you don't know where your final destination is, like in some network where they want to start, for example, a virtual circuit. You want to communicate with somebody, you don't know where they are. It's no problem. Flood the request. It will go to everyone. And the other one will respond back to you. or if you want to, so it's possible to find every node, and you can reach every node, and even if some links break down, it will still work, and also you can get rid of those packets. So there is another technique. Time to live is just one technique to get rid of too many, the extra copies. The other technique, they said, every router, remember in the immediate past, like in the last second only, keep numbers of those, the numbers of those packets, the actual packet number in the last or in the immediate past. And if you send a copy this way, it comes back to you this way, because every node will send a copy everywhere, except where it got it from. But it's very possible this guy gets a packet, sends copy that way, copy that way, copy this way. This guy got this copy. It will send a copy that way and a copy that way. And then both of those will end up sending everywhere. So this guy sends a copy that way, it will end up coming back to it for certain. So if we know, if this guy keeps the number of that packet, so if it comes back again to it, do a check on that list that gets just moving all the time, updated only for the last 1 second. It will find, oh, I've already had this packet only a quarter of a second ago, or 10 thousandths of a second ago, but then I will not forward it again. Well, that's a second technique or mechanism added to flood routing to reduce the number of packets. But flood routing, right now it's never used as the main routing kind of algorithm, but it's used as a secondary part in case breakdowns or in case of if you want to broadcast something to everybody. It's a great way. You do it once and that's it. So that's called flood routing. The next one is called centralized routing. Why? Because what's the problem? See, that we know what the best system is. It's the adaptive one. If there's a breakdown and if we know about it, we can avoid it. If there's a lot of traffic in one area, we can start diverting traffic away from it. It's called adaptive. And this is what most successful networks use, an adaptive routing algorithm. But the problem with it is that we said they have two problems. Anybody remembers what are the problems with adaptive routing algorithm? Think of one. Pardon? It collects a lot of information, but what's wrong with that? What's the problem in that? What's the... Say again? Yeah, one of its problems, it needs a lot of processing to do a lot of calculations when it gets the new information every 3 minutes or so, and it has to update the tables. So that's a lot of processing power. That's one of the problems, yeah?
The second one is the cost of the transmission channels.
And the second one is that because it collects a lot of information very frequently, it uses the transmission channel. Instead of leaving our transmission for data, for user data, now it's using a lot of it. So another system came up, not like flooding, but this is called centralized. And centralized said, we'll solve one of your problems. Pick one good processor, one machine, buy one good processor, and stick it somewhere in the network, somewhere in the middle of the network, ideally. And you tell routers you don't have to do any processing. I'll do the processing on your behalf. So just send the information to this device. So every 3 minutes or so, all routers send their information to that device, all their routing tables, existing route table or breakdowns or report. So any information goes to that device every 3 minutes, and that device, that's all it does. It has powerful memory, powerful CPU, and runs this application and builds all the routing tables for all routers. And it does it quite efficiently, and then sends them out. So you send the routing table to every router. Individual, personalized, made to fit kind of personal routing tables for individual routers, and send them out. And that's how it works. So that's centralized routing. One device that's allocated in the network that will do all the routing. Now let me just define two terms. And if you ask what's the function of a router in general? A router, anybody knows what the function of a router is? A router has two functions. One is the main one, one is the secondary one. I come back to you. You didn't ruin my lecture. Anybody knows what the function of a router is? What's the main job of a router? Routing, did you say? Oh, redirecting packets. Packet forwarding. Yeah, is that what you, are you sure?
Yes.
What about routing?
Routing is the one, the primary.
Okay.
Finds the shortest route within the network.
Okay, that's the secondary. Okay. Every router, guys, has two functions. The main function of every router, it's called packet forwarding. That means a packet comes on this link, it has to forward it to that link or wherever it needs to go. That's called packet forwarding. And this is a very fast operation. It receives the packet, it opens the header, looks where its IP address is. Where do you want to go? And it goes to the routing table, or its routing table, hopefully, and checks this destination will be an IP addressing. Oh, there it is. You want to go there? Here it is. I'll send you to G, and it will send it to this link. And sometimes they don't write, of course, here they write port number 012. It has 3 or 4 ports, and then it sends you to this port or that port or that port. So that's called packet forwarding. It's a very fast operation. Receive a packet, and it probably you could actually have 1 million packets passing through a router a second. Opens the packet, look at the IP address, go to the routing table, find out where it is, where I should forward it. You know, we don't even tell it how much it's going. Oh, I need to send it to port 2. Just puts it there in the queue for port 2. The transmitter or transmitter get the next one, and so on. So this is the first and main job of a router. It's called packet forwarding. The other job of a router is called routing. And what's routing? I thought it's, finding a packet and putting it in the right route. No, the word routing means building up your routing table or updating your routing table. That's what the word routing, building the routes. And that's the one that costs a lot of information to be collected and a lot of processing. And that's what routers really, every router, almost in every Cisco network and other network, has to stop every now and again and do that processing. It takes a lot of processing power. So centralized routing, and hence comes in centralized routing. So centralized routing say, don't worry about it, I'll do it for you. So we have one big powerful machine. It could be a router that has an extra power, or just a separate device, a server that does nothing except routing. And what's routing again? Can you tell me what routing is? What is routing? What do we mean? We say, now if you're asked in an exam, what's the definition of routing?
Updating the routing table.
Exactly. Not finding the best route. Building or updating your routing table. That's what we call routing. What's the function of finding where to send a packet? What's that called? Packet forwarding. So these are the two jobs of a router. Packet forwarding and routing. And packet forwarding is the main job that every router in the world does. Doesn't matter in any network in the world, whether they do centralized packet, whatever, any kind of routing, the router will forward that packet. It's the routing part that most routers do, but sometimes, like in centralized routing, we'll have another device that will do it. Yeah.
Just building and updating the
Routing
routing
tables.
tables, does that involve collecting all the information?
Most of the time, yeah, of course, yeah. Unless that's to change the information, you need to have some new feedback, some values, delays, breakdowns, something else like a new machine, a new router was switched on, or a new link was broken. Now it's back connected. So that will require updating your routing table. Yeah. And how do you know that? You get information from other routers sometimes. Okay, so is centralized good? Centralized routing, does it have advantages, disadvantages? Yes, it has good advantages. The main advantage is that routers are now, they don't have to stop and do this heavy process. They can use all their power to forward packets. And that's what we really want routers to do, packet forwarding. We want them to keep on sending packets around. So that's the main thing. And also, they don't need to exchange information with each other, but they need to send information to the centralized device. And routing cable calculations, no, the processes, routers don't have to do that anymore. And routes produced, and guess what? Routes that are produced by one machine, they never seem to have conflict. Remember the normal routing, where every router does its own routing, if we were all routers in a network, we'll exchange information, and maybe at periods of time or whenever something changed, we all stop and calculate and update. Each router will update its own routing table using the same algorithm, of course. But sometimes there might be a conflict because two different programs or two different machines have produced the algorithm. And they might have got an error in the number of delay and from that end, or for some reason, that router thinks in order to send a packet to that machine, send it to me. But in my table it says, in order to send a packet to that machine, I better send it to you. And there's a conflict. So you send me a packet and I send it back to you and we keep exchanging it. That's because two different parties or machines have tried to produce a routing system or a routing for everybody. And sometimes there may be a conflict. Here, it's less likely to happen that we will have conflicts because the whole thing is done by one machine, by one algorithm. But, it's not really a major thing. Most routers, they actually don't allow them to go online unless they've been tested heavily and approved. But still, you never know. There might be some errors that were not discovered through testing. Centralized routing has a lot of issues and problems as well. And it doesn't adapt quickly, takes a bit of time. And sometimes, remember when the centralized machine fixes and calculates the next routing table for the next period of time. Imagine the device is here. That's our centralized router. That's the device or the server that actually builds the routing table. They call it the control center, routing control center. If that's a device that collected and built the tables and will send them out, guess which router will get the first table, the new set, the new version of the tables? A will get, because it's the nearest to it. And this one here, or a remote router even further away, will get the new version of the tables maybe a little bit time later. Between this router getting its new version and that router still using the older version, sometimes there might be a conflict between the old and the new. And for that brief period of time, it's only half a second or a quarter or less than that. This will be using some routing system, and that will be table, and that one will be using the older routing table, and there might be a conflict between them for a little while. So that's just it can cause a problem for a little while. If there was a major difference between those two routes, maybe this router broke down, then there will be a major change. We won't be sending information. This one used to send information this way. It can't send it. You have to send it that way or this way, and so on. So that's one of the little problems with centralized routing, but it's not really used a lot either. Okay, only the topics that I'll talk about that we need to concentrate on. So hopefully the video is working. Right, so we have just the definition of routing and forwarding, and there are two different definitions. Remember, a router doesn't need to know about all the routers in the world. It go up, there's a hierarchy of routing. Maybe in a college or you'll have a number of routers, but if you need to go outside the college, there's one or two routers that are our default routers. Every time if you do IP config on your computer, you'll find your IP address and you'll find your default router. So that's the information that you need to send if you have to send anything outside our network. Otherwise, your routing table will deliver to all your local users. If you're going to send a message to somebody in Australia, your router doesn't know where that is, but it knows it can give it to this router. This router will bring it, say, whatever, let's say Ireland and Britain and France, are there few routers that it can move, you can send it to that one that so eventually it's going to be delivered. So you go up or down through the hierarchy, but no router needs to know more than 5 or 6 or 10 maybe addresses at the most. So routing tables should normally be kept short. So let's get to adaptive routing. This is really the serious one. This is the one that's used by over 95 or 98% of networks in the world. They use adaptive routing. And just to bring it to you, quickly, there are two routing algorithms really over since the 70s, since the very start of networks. There's a routing called distance vector routing algorithm. And it took about 20 years, but it developed into something else, and it's called the link state routing algorithm. And they're both in use. The link state is the one that's in use, obviously, in many networks, including Cisco networks. So the major difference between them is that first, the distance vector is an older system. It started very long time ago. And it's based on the number of hubs. At that time, back in the 70s, all links probably had the same speed and the same, capacity and the same bandwidth. So it didn't really matter that much at that time. But then fiber optics came out and all that, so it's really, the link can make a huge amount of difference in speed. So the new systems, they actually take into consideration the type of the link that's available and the speed of the link. But the older system is just number of hubs. How many hubs? This one has 3 hubs, this one has 2 hubs. They bring us to the same destination. Take the one with the least hubs. But right now, you could go with the least hub, but it's really slow. It has twisted pair cables on those 2 hubs, while fiber optic cable take you through 4 or 5 other hubs, but you get there quicker. So you might decide to go with the bigger hubs, but faster or bigger bandwidth and all that. So the older system as well, what you need to know is they both are adaptive routing, and they both need to collect information, but the way they work, the main idea, that the biggest difference in the way they work, and this is the older system, it's called distance vector routing algorithm. What it does is the way it's the basic difference from the newer system. It says periodically, like every 3 minutes or so, and it's set between 30 seconds, 1 minute, 2 minutes, but usually it's anywhere between 30 seconds and 3 minutes. Periodically, every router will share its knowledge about the entire network to its neighbors. So every router has a big routing table with every router in our network, and it keeps updating it and sends it to its neighbors only. If it only has 2 neighbors, send it to those 2 neighbors, but also those 2 neighbors will send theirs to their neighbors. So you share information about everybody with your neighbors. That's like in a house, somebody's watching everybody, all the neighbors in the street, and they go and meet with their neighbor, cup of tea. Did you hear that? Did you hear that house number 17, this, and house number 12? And we have a lot of people that do that. That's talking to your neighbors about everybody, right? This concept is important because if I was at distance, if we were in a distance vector routing, and if I were a router and I had another neighbor here, another router, and the link broke down, or the router, my neighbor, stopped working. So I'll put that in my table. Hey, that router is no longer available, or whatever it is. And I'll send this information to my neighbors. So after 3 minutes, my neighbors will know about it, and they'll update their routing table. Now, the next exchange that happens after 3 minutes, these neighbors will notify the other neighbors. And then the other neighbors update their routing table, and after 3 minutes, they'll know, and they keep passing the information. So something that happens beside me in distance vector routing algorithm will take a long time before it reaches the other end of the network. That's how it works, and that's one of its major problems. Now, let's look at the other one that's called the link state routing algorithm. There is the link state. Sorry. Okay, the link state routing algorithm, it's also an adaptive routing algorithm. It's the more modern of the two, and the way it works as follows. If I find it, I'll read it. If not, somebody has removed my slide, right? There it is. Okay, the link state routing. Okay, is it time for a break?
No, I was just stretching.
Okay, yeah, almost. Instead, okay, they do the same thing, they collect information. The link state routing doesn't collect it every 3 minutes, only whenever there is a change in the network. If a router breaks down, or anybody knows there is a problem, they will actually exchange information. But anyway, now, back again to the same situation. I have a router beside me and broke down. So a link broke down beside me. The way this system works, the link state, every time, periodically, or whenever something happens at a certain event, every router will collect information about its neighbors and tell everybody. So it's the other way around. Remember, the distance vector, the old system, collect information about everybody and tell your neighbors. Only send it to your neighbors. This system works the other way around. Collect information about your neighbors and broadcast it to everybody. It's like the guy who talks about their neighbors. Now it's bad, but it actually works better because taking the same problem that we had, there's a router beside me, broke down. I'm the only one who knows about it in the network. It's one of my neighbors. So that's a change. Or at the next time of exchanges, I have that neighbor and the other two neighbors. So I just collect right information. This neighbor, IP address, this is the cost to go to them. This neighbor, so it's very short pieces of information, put them in a packet and boost. Send it to everybody. Everybody receives it immediately. So everybody knows about this broken router very quickly. So that's information travels a lot faster using the newer system that's called link state. So just remember what makes it faster. Remember the way it works. Remember the way that both of them work. One of them, the old system, it's called distance vector. It learns about everybody and sends the information to their neighbors. But if the change happens, you notify your neighbors, and 3 minutes later, the neighbors notify the neighbors, so information travels slow. Whether it's good information or bad information. Like if a new link comes up here, I know about it, I tell my neighbors. 3 minutes later, the neighbors tell their neighbors, so it takes a long time before everybody knows about it. The link state is the newer system. It was developed maybe it was developed right from the start of that one, but they kept developing over 20 years or so. It's still developing. This is called the link state. All you do, collect information about your neighbors and send it to everybody. If my neighbor here started becoming slow, just the next year, I'll send information to everybody. Everybody knows now this neighbor has got slow, and very quickly. Yeah.
Why would this be taken over the centralized? Because I think the issue with taking the centralized is that you have the closest node to it without taking over the faster and one like everything. But then with this one, is then broadcasting to all the neighbors, so it would be exactly the same.
Yeah, but the link state broadcasts to all the neighbors very little information. It broadcasts to everybody, but only tells them about the neighbors. For example, if I had two routers, that's all I need to send. The IP address and the cost of those two, instead of the full routing table that I need to send. So link state routing, guys, has a number of advantages compared to the distance vector. You need to know, comparing those two. Obviously, which one is better? This time we're going to say it doesn't depend. This link state works better because the information it exchanges periodically is big piece of information because it has to send the full information about the entire table. Every router sends its full entire table to its neighbors. The other one, the newer one, the link state, only sends information about its neighbors to everybody. So the routing packet that goes out is much smaller. The other thing, distance vector routing does this every 3 minutes. This one does it only if there is a major change. If there is a change in the network, like noticeable like delay or breakdown or something like that. So there's less, updating going. And also, the information is discovered and spread very quickly. Like if something breaks down, everybody will know about it using this system than the other system. The other system, it might take 15 minutes before a router knows about a broken link here. And yet in those 15 minutes, you can think of the millions of packets that will be directed towards that broken link. So with link state routing, it will get the information quicker. Okay, so these are really the two major, or the two pieces of information that you need to know about the link state and the distance vector routing algorithm. And this is some of its advantages or some of its properties, the link state. It stabilizes quicker. See, if a link breaks down, what do we mean by stabilizing? Or they all kind of know about, like if a link breaks down, you want all the routers to know about it and start directing traffic away from it. With the link state, once you tell them, they will update their routing table. So they get in line, in sync together quicker. With the distance vector routing, you know about it, you update your routing table and you tell your neighbors. The other neighbors will do it after 3 minutes, and then even the further away neighbors will take them another 3 minutes to update their routing table. So it will take them a long time before they all match their routing. The remote one is still sending information this way. When you say, that's broken, go back that way. Eventually it will do it, but it'll take a long time. But with the link state, because the information is broadcasted immediately, they'll all update their routing tables, and their individual routes will match and will harmonize and will get better together, quicker. And it scales over. This one scales better, the link state scales better, that means grows bigger, can handle bigger networks than the distance vector routing algorithm. So the distance vector, this is the older system. The disadvantage is it's slower to converge. That means all routers to agree on something that happened. Like if something breaks down, you want to update your routes, this will take longer to do it. It's at risk from counter to infinity problem. That's a problem. It happens to it. They noticed it that every time a remote link breaks, like a router that only has one link to the rest of the network, there's no other way of reaching it. If it breaks, every other network or every other router in the network shall say, oh, my cost was 3 hubs there, is going to go to 4. Another one says, and then 5. So instead of saying that's not available, that has another problem in its algorithm, that the costs start incrementing, and it keeps counting until it reaches the maximum number available before it actually says, oh, that's not available. So it's called count to infinity. You don't need to worry about it, but you should know that it does exist. And it creates more traffic than the link state, because you know the reason why it creates more routing traffic? Because each router has to send the full routing table about everybody to its neighbors. With the newer system, the link state only sends information about its neighbors to everybody. So the routing packet is much smaller. Hub counts updates take place on periodic basis, even if there are no changes in the network. So you keep, even if there's no change in the network, they keep sending information, they keep stopping and doing processing, and they come up with the same figures again. So it lacks that kind of intelligence. And for larger networks, distance vector routing algorithm results in much larger routing tables than link state, and each router must know about all the other routers, and this can lead to congestion and so on. So this is really all you need to know about routing.
Can you have like a hybrid of link state with centralized, where you just send the updates to the centralized one?
Yes, I was told you can have multiple routes in some networks, but I'm not sure if distance vector would be the choice. Maybe flooding and link state are used on Cisco. I'm not sure if they use the distance vector. Okay, guys, so you should make sure you can create a routing table for a particular router on a network, and make sure you understand the general concepts of adaptive routing and dynamic or static routing, and the differences between them, and the two routing algorithms, distance vector, and link state routing algorithms. Right, we take a break and we come back. 5 minutes break, gonna start another topic. Stop sharing. Stop.